This is our fourth class, end of second week. So far we have learned about vocabularies of the words that are used to describe motion, right? And then we talked about how to represent them in graph and motion diagram. And we use velocity versus time graphs to write down the kinematic equation. And these kinematic equations basically relates those quantities, physical quantities that is used to describe the motion, like displacement, velocity, acceleration, time interval. So these equations are nothing but just the combination of those. So when you change one thing, let's say, how the another thing gonna change? For example, when time changes, how the speed changes or displacement changes, or the, let's say, is acceleration changing? And by the way, in kinematic equation, acceleration are constant. So that's why they are not changing. And that's why you don't see initial acceleration or final acceleration in this equation. And after writing this equation, we learned how to read this equation properly so that we know how to use them, okay? And I have written them here. So just wanted to remind you. Another thing I like to point out is that this equation, when we say in a direction, we can add that direction here. So for example, if it is in x direction, you can put x subscript in each of those vector quantities. Okay, time is not a vector, so you don't need to put x or y direction. Okay, and if we are looking at y direction, for example, or any other direction, we can say, okay, this is y, this is y. So that's why you see in equation sheet I have posted on Canvas, they are written like, with the subscript. I think subscript used are basically x, but that x could be y, okay? And after that, we did a practice on actually how to, let's say, use this equation to solve problem. So, and these are my suggestions. These are my suggestions, to solve problem using kinematic equation or actually any equation. So first you want to read the problem. So far we have only talked about kinematic equation. We haven't talked about dynamics or energy and so on. So only thing you're going to be using for now going to be kinematic equation. But once we cover all those things, then it becomes a little bit harder to choose which concept to use. And by reading this whole problem once, that helps you to determine, okay, what's the physical concepts are there, okay, to solve any problem. So read the problem and sketch the situation. That's what I have shown here, okay? And then reread the problem a sentence at a time. And then list the knowns and unknowns. So those are the steps I talk here, right? Since we already went through this in last class, I'm just reviewing it. So that's why I'm not going in detail, okay? And once you have written them down while writing, make sure you are writing them with proper notation. What is proper notation? The notation we've been using in this class, the notation you find in equation sheet. That way, now when you look at the equation sheet, okay, you can decide which equation to pick. Okay, once you have decided which equation to pick, or sometimes, just like we saw last time, you may have to pick more than one equation, okay? So once you decide, use those equation, and physics is done. Once you have equation, remaining is just mathematics, and in this case, algebra. Okay, after that. So that's how we solve problem using kinematic equation. So here is a question for you. So in this case, what you have is two objects. So can you just use one equation for one object A and another object? Decide that. Okay. So how do you decide? Look for, just like first for first object, let's see what are the given thing and which equation you plan, which equation is suitable to use. And then redo that for B, right? Check that and see if you can use the same equation. If same set of things are given, then you can use the same equation. If same sets are given and same thing you are asked to find. So for example, in this case, it says distance traveled by car A, giving time, and then compared to distance traveled. So both of these are asking for distance traveled. And in this case, both cars are just moving in one direction. They are not reversing the direction. So that means distance and displacement, they're going to be same, right? So with that said, I'll let you work on that. And meantime, I'll also start the clicker. Okay? So you have 3 minutes to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, I see a question. How do we choose an equation? Yeah, we briefly talked about that last class as well, and I'll talk about that here as well. Okay, let's see what we got here. So mostly B, and there are C and D as well, and there is 1A. So how do I know it, right? How do I choose how to solve an equation? So before you can choose equation, this is the process you have to go. Which one is known, which one is unknown? So if you look at all these, what you see is there are 5 different things, okay? Initial and final velocities, which is not listed here. I did not list the final velocity because in this case, we don't know final velocity and it's not asking about final velocity. So that's why final velocity goes in I don't know, I don't care categories, okay? So in this case, initial velocity. So both of them starts from rest means it's going to be 0, 0 for both, okay? And then it's it says, okay, same constant acceleration. So in this case, it does not give you the value of acceleration, but it tells you the acceleration is same for both of them, okay? If one is accelerating at 1 meter per second squared rate, another one is also doing the same, and so on. So we don't know what that number is. And to answer question, maybe we don't need it. But we have this information. Whatever acceleration it has, the other one has the same acceleration. So I'm just writing A for that. Okay. And then there is time interval. So for car A, 1 second, and for car B is 2 seconds, right? And for both, oh, what happened? So for both cars, what happens? We want to know the displacement. So now, once you have listed, look for these 5 things for each problem. Okay, look for these 5 things and write them down just like I have done here. And then after that, that helps you to choose equation. So how do you do it? So there are these 4 quantities that are either known or we are asked to find. So final velocity, we don't know, we don't care. So that means this has a final velocity. So maybe we don't care means we do not want to use that equation. Okay, let's see if we can find another equation that's better than this. Another thing to avoid this equation is that it doesn't have displacement in this equation, and we are asked to find displacement. So if the equation does not have displacement, we cannot solve for it, right? So this is no go for this problem. That's how we choose it, right? And then this one has a displacement, good start. Initial velocity, yeah, we know initial velocity. Time interval, yeah, we know. Acceleration, although we don't know value, we have idea that both of them have same acceleration. Okay, great. So this checks in everything. So this is the equation to go. Just to make sure that, see, we can use third one here. Again, there is final velocity, which is we don't know, we don't get care category for this. And then there is no time here. Okay. So that's why this is not the equation to use. Okay. So once we have that, we decided, okay, we want to choose this equation. Second equation in this list. So that means now I want to look at closely. So first, what I like to do is, okay, VI is 0. So that means I don't have to worry about this term. So basically, this equation becomes just this once the initial velocity is 0. So I'm not plugging in time yet. I don't know A, so I cannot plug in, right? But I know 0, and whenever it's 0, I plug in that one first, and I don't rush to plug in other numbers, even if I know those numbers. Okay, that's how I like to start. So I copy this equation first, and then say, okay, this is 0, and then that. Okay, so that's what I mean when I say, okay, start solving problem by first writing the equation. Do not just scramble with numbers. That's not going to make any sense. Okay. So yesterday I received email saying, what do you mean by start by writing equation? That's what it means. Okay. Write the suitable equation. So for example, if you are finding slope, write the equation for slope. Rise over run, or displacement over time interval. So that's what I mean when I say write equation first and then plug in numbers there. Okay, so that's what it means. So now what we have is this. So we can actually write this equation for car A and car B separately and solve for the things that we are looking for. But let's see if we can do it even without writing this explicitly for one or the other one. So what do we see here? This half is number. It's not changing for A or B. A is also a constant number, although we don't know that number. It says it's a constant. That means it's a number. And it's the same for both. So these are not changing. So displacement for car A and car B is different because time is different. You see that? So only time is making the difference. Do you recognize that? So that's how you need to look the equation. That's how you need to read the equation. Okay. Only is the time that's making difference. Now, looking A versus B, what's the time difference? One is 1 second, another one is 2 seconds. So we want to look at in terms of ratio because we are comparing, okay, rather than subtract. Look at the ratio, 1 versus 2. 2 is double of 1, isn't it? 2 is double of 1. So car B is moving double time compared to A. Doesn't matter what time it is for now. Even so, let's say if car A had moved 2 seconds and car B had moved 4 seconds, time is still double. Do you see that? A2 versus B4. So time ratio is still double. So that's how you need to think because we are comparing. When we compare something, what do? We divide one by another one. That's how we compare things. Okay. So let's say if my height is 2.5 feet, or let's say 3 feet, and your is 6 feet, your height is double compared to mine, right? Mine, isn't it? 6 versus 3, double comparison. You have double height, or I have half height compared to yours. So that's how you need to think when you are comparing one versus another one. So now time is double. Time, when time doubles, double means 2 times, right? 2 times, let's say. You don't need to write this. It may be a bit confusing because x versus times, okay? So this is 2 times. Let's write 2 times. That way it's not going to be confusing. Then what happens to the time squared? See, the equation does not have time, not just time, it is time squared. Do you see that? It's time squared. So when time is double, what happens to the double when you square it? It's going to be 4. T2 means t square is 2 square, right? When you square t, and if t is 2, then t square becomes, let's say, 2 square, which is 2 times 2 is 4. So 4 times. See, that's how you can see it's going to be 4 times. If time is double, you're going to go 4 times. So if acceleration of your car is same, the distance traveled by you becomes 4 times larger every time you double the time. That's what this equation is saying. I'm not saying that. That's what this equation is saying. And we are using this equation to get that information. Okay. So that's why this 4 times is the correct answer. That's what this equation told us. Okay. And if you want to do for both cars, yes, you can do it. So let's do that one as well. So for A, let's write down this equation for car number A. Okay. For car A. Displacement for car A is half A. We don't know A, but we know T for A, which is 1 squared. So it is simply half times A, isn't it? So now for B, let's repeat that for B. Half A, see, they are same. So only thing that's changing is time, which is 2, 2 is squared. Okay, so that means 4 times half A. So it may look silly. Why am I writing 4 times half A? See, it's easier to compare that way. See this halfway, half A, they are same. And you can see delta XB is 4 times larger than this one. Or you can divide one by another one, everything cancels except that 4. So it becomes 4 times larger, okay? So what do I mean by that? So for example, I can do delta XB, divide that by delta XA. So this is called dividing one equation by another equation. When you divide one equation by another equation, what happens? Left side divides the left side and right side divides the right side, okay? So that's what I'm doing. I'm dividing the left sides of both. So for B, this is 4 half A, 4 times half A. And for A, this is simply half times A, right? And you can see this half A, they cancel, giving you just 4. So that gives you 4 times displacement of A. You see that? So this is systematic way of doing it. But just by looking at this equation and saying, hey, time is doubling, so it better be 4 times. If the time had triple, let's say 3, if for car B, time was 3 seconds, let's say we waited until 3 seconds, what would be the answer? 3. Time is 3 times, means time is square going to be how many times? How many times? 9 times, right? Because 3 square is 9. So the answer would be 9 times more, and so on. What if we needed to solve for A? None of these equations solve for A. So yes, so if you need to solve for A, maybe you need more information. Maybe it's going to tell you something different thing, okay? Maybe displacement will be given or final velocity will be given. That's a good point. So I'm answering that question from Nicholas from the Zoom, okay? Okay, so this is how we solve equation, right? I mean solve problem using kinematic equation. And I have one more example before we move on to the regularly schedule, slides for this class. So these are leftover from last class. Okay, since we are doing this using kinematic equation very first time, I thought we should give a little bit more time for that. So here is a question. So what's the situation here? There is a runway and jet starts from somewhere and takes off somewhere there. So they're going to be initial where it starts and they're going to be final, right? So that's the SketchUp situation. So what are the things among these you know in this problem? Okay, so that's what you want to see. And again, you have 3 minutes, and for this, you may need calculator. So because of this conversion here, it's rounded. So because of that, you may not get exact number, but you will get close number. So find the number that's closest. That's why I'm writing approximate. We have only 5 things. Among 5 things, what are the things you know? List them, okay? If you know 3 of them, maybe you can solve for 4th one because these equations have only 4 in each of them. Okay, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Yeah, this may have been a little bit, bit tighter. I mean, probably you could have used a little bit more time. So we see C and E, C and E. Yeah, I don't know the answer, but I know how to do it. So among these 5 things, let's see what are the things we know. Initial velocity. Do we know initial velocity in this case? A jet or plane is trying to take off in a runway. Initially, most likely it is not moving. So yes, 0 makes sense. Okay. Final velocity. So it says jet must reach a speed of that much to take off. So that means the final speed is that. Okay, after takeoff, what happens? We're not interested. We are just interested in the motion, during which this jet is on the runway. So this is the final speed. And the available runway to take off is only this much long. So maximum it can move before it can take off is that much. So displacement is just that number. Okay. Acceleration. Oh, that's what we are looking for. Here, time is not given. So don't know, don't care. So now we need to focus on equation that has these four things. Let's see if we can find a single equation that has all four of them, okay? A single equation that has all four of them. So this one, oh, this has time, which is, I don't know, I don't care, both of these. Looks like these not good to solve in one step. Now let's look at this one here. So final, yeah, we know, checks out. Initial, checks out. Acceleration, yeah, that's what we want. And displacement, we know. So that means all these fours are in this equation. So that's why this is the equation to use, okay? So now, so I start by copying this equation. Bf squared is Bi squared plus 2a times displacement, 2 acceleration times displacement. So initial velocity is 0. So that means it's simply 2 acceleration times displacement. And I'm solving for acceleration. So that means I need to get rid of this 2 and displacement from this side. So that means I want to bring that to this side. So they are multiplying to the acceleration. So that means they're going to come here and divide. Okay. So that is the acceleration. So that means now I can plug in this number here, which is 73.8. And I need to square that. So what I'm going to do is I'm going to write that in this side here, 73.8 meter over second and squared, and 2 times displacement, which is 301, unit is meters. So there is a meter, there is second, so it's going to be meter square, second square, and one of the meter going to cancel, so we're going to get unit meter over second square, and that's the unit of acceleration. That makes sense. And we need to square this, and we need to divide that by this 602. Okay. So what are we getting? Which one is closest? So I see there is one response that says a big number. Probably you forgot to divide that by 602 here, right? 2 times 301. So mostly I'm seeing E. So I believe in you, you believe in you guys. So that's that. Okay. So that's the kinematic equation, folks. So that's how you use it. So you wanna, so I have solved at least one problem, I think, in the note. See if you can solve that without looking at note, right? Now, and even, I mean, now you can solve that, hopefully. And then come back and solve these problems without looking solution. See if you can get them, okay? So that's the beginning. And there are solved problems in our textbook, and our textbook is OpenStax, college algebra, right? So there are solved problems there. Look the problem, do not look at the solution, do not look at the solution, solve it, find the answer, see if the answer matches with yours. Okay, so that's how you want to practice. Okay, and we're going to be doing this kind of practice for the thing we're going to be talking now, which is free fall, which is also use of kinematic equation. Okay, so only difference from this one to free fall is now we're going to be looking at motion in vertical direction. Okay, vertical direction. And in that case, turns out the acceleration is known. We know the acceleration. So acceleration going to be always known for that. So that you need to keep in your head. It's not going to be in the problem. Okay. Once you know it's free fall problem, you know the acceleration. Okay. Speaking of acceleration, let's see motion diagram of an accelerating object. Okay. And in this case, what I'm saying is acceleration is in the opposite direction to the initial velocity. So here is my object, and these dots, white dot, is the motion diagram. The dot represents the motion diagram here, this white dot. And I also have this graph, position and time graph. So I made this animation to show you how does the motion diagram of an object that has acceleration in opposite direction looks like. Okay. And similarly, how does the position versus time graph of that motion looks like? That's what I wanted to show you. It's a short animation. If you blink, you may miss. Okay. So let's run this animation. See how the separation distance between white dots, they are getting smaller and smaller. You see that? And they are getting very close, means the object is about to stop. So object is slowing down. You see that? So acceleration is opposite direction of motion, and that's what we learned last class. When acceleration is in the opposite direction of motion, motion slows down or object slows down. We learned that last class. Do you still remember? Hopefully you do. Okay. If not, remember, when acceleration is in the opposite direction of motion, object slows down. Okay. So what happens? The object slows down. So we can see here, position versus time graph. If we want to find speed or velocity, what do? We draw a tangent line, for example, in a couple of places. And you see this line is sloping. See, it was something like that. Highest slope, less slope, and now this is flat with respect to time axis, means zero slope. Zero slope means V is zero, because slope of the tangent line is the velocity at that instant or instantaneous velocity. So this is zero here. So it was moving, now it stops. But there is still acceleration. Object is still accelerating. And what is the direction of acceleration in this case? This way. And direction of acceleration is not changing. Okay, it's not changing. Acceleration is still in that direction. How this object gonna behave after it stops for a brief moment? What's it gonna do if it is still accelerating backward? So for example, for a moment, velocity is zero. Okay, velocity is zero. And now acceleration is in that direction. How would the motion of this object gonna look like? It's like car is not moving. Now you hit the accelerator in your car. Car was not moving. Your engine is on. Okay. Now you hit the accelerator. What happens? car moves forward. Okay, car moves forward, right? In the direction of acceleration. So speed gonna increase now. In what direction? In the direction of acceleration. That's what we can tell. And see what does this block does now, this block, big block. So let's look. See, now it starts moving backward. So direction of acceleration is always same here, the backward. You know, it was opposite to the initial motion. Okay. So you see that? So that's the position versus time graph. And if I were to make velocity versus time graph, how it's going to look like? Let's think about it. So it starts with high velocity, highest velocity. And if we say up as a positive, then we say, okay, it starts with maximum positive value of velocity. And then velocity is decreasing. And velocity becomes 0 here. And then what happens? Once it goes, it's downhill now. The tangent line shows slope is downhill, means negative. So that means it goes to the negative side. So this is going to look like this, velocity versus time graph. Okay. And the acceleration. If I were to make acceleration graph, how is it going to look like? Acceleration is fixed and it is backward. So if forward is positive, backward is negative. So that means acceleration is negative and the acceleration is constant. Let's say it's constant. It's same all the time. See, velocity is changing, but acceleration is not changing. Whatever it is, remains same. Okay. So that is your acceleration versus time graph. This is your velocity versus time graph. Okay. So now, we have that kind of motion in nature. Okay. So what kind of motion I'm talking about? Where the acceleration is always, acceleration is opposite direction to the initial velocity. So what is that? If I throw this ball up, once it leaves my hand, what happens? It becomes free from my force. See, once it leaves my hand, I'm not applying force anymore. By pushing it, what did I do? I gave initial velocity to this. So just like that block was moving with initial velocity at the beginning, now it will start moving with initial velocity. Okay. Oh, and then it came down. Okay. So just like that block came back, this is coming down too. So when it's going up, what happens? It's slowing down. And at certain point, it stops, and then it starts coming down with increasing speed. So when something is moving under only the gravity, we call that free fall. Okay, we call that free fall. Even when object is going up, we still say fall. Ooh, that's kind of weird, right? But it's a free fall. Even when it's going up, we don't say free rise. We say whole motion as a free fall. Okay, whether it's coming down or going up and coming down. Okay, it's a free fall. That's the kind of motion we're talking about. So here I have an animation which is similar to what I'm talking about. So I'm giving a push to this ball and see how this ball goes up. Doesn't want to go. Okay, goes up and then comes down. So if I were to make motion diagram, this is how it looks like. At the beginning, it was moving faster. So the dot, let's say if we start from here, what happens? So the separation is larger and getting smaller and smaller and smaller, right? So that's the motion diagram for object That's in free fall and going up. That's the motion diagram. You see that? And now, when it's coming down, what happens? So after it briefly stops, it starts moving backward. So what happens? Downward. So you see, it now is speeding up. It gets larger and larger speed. Actually, it turns out what happens is, whatever speed you release this ball with, when it arrives back to your hand, the speed of the ball gonna be same. That's how it works, actually. Okay. But that's not the thing we are trying to find here. We are looking at the motion diagram. So we can tell, the acceleration by drawing the motion diagram. We can use motion diagram and draw change in velocity vector, and that gives you motion diagram, isn't it? And we have learned that. So for example, if something is moving in horizontal direction, and if the final velocity is smaller, see the arrow is shorter, right? If the final velocity is smaller than initial velocity, then you line up tails together, and then delta V is now drawn from tip of the initial to tip of final. So that's why it is backward. See? So it's backward. And it can be object, on the slide. So for example, let's say you go to the playground and you push a ball on the inclined slide. What's going to happen? It's going to slow down and stop and come back unless you throw really hard, okay? So if you just throw a little bit, what's going to happen? It's going to go up and then kind of come down. So that means while going up, it slows down, isn't it? So that means you can draw delta V for that one as well. And it's pointing backward or opposite of initial velocity. And same thing is happening here as well. Okay, when it is going up, see how this second one, VF, is shorter than BI, just like we had there, right? So what happens? We have this delta V pointing down. And what does the delta V or change in velocity means? This gives us the direction of acceleration, okay? Acceleration, because acceleration is change in velocity over time interval, okay? So direction of acceleration is same as direction of change in velocity, not velocity, but change in velocity. And we spent quite a few time last class, okay? So that's why I'm writing that this acceleration in y direction now, because I'm assuming this as a y, and let's say that is positive, okay? Up is positive in this case. So in that case, acceleration is down. Direction of acceleration is down. What's the value of acceleration? Turns out we can measure it, and it turns out it's same for everything, all objects, okay? So that turns out to be 9.8 meter over second square. So G is always 9.8 meter per second square. What is G? G is value of acceleration, just the notation for value of acceleration. What is G? Value of acceleration due to gravity. We call that acceleration due to gravity. So G does not have positive or negative sign. G is this number, so you do not want to write G like this. Plus or minus sign. for vector, in this case, acceleration is vector, means direction. And that we are writing here down. See here? We wrote down. Now, what we can do is, okay, we can say, okay, AY is now, if we do not want to write down, and if we want to use this in the equation, then of course we need to replace down by positive or negative sign. In this case, we are saying up is positive, so down means it's going to be negative. So this negative here means down. So this negative came from this direction down. This negative is not the negative or positive of G. No, G is just a number, value. Okay, so keep that in mind. Sometimes students say, okay, G is negative. G is not negative. G is just a number. Okay, what is negative? Acceleration is negative. What is G? G is only value of acceleration. So that's why it does not have positive or negative. So direction of acceleration is positive or negative. And how do we denote acceleration? Not by G. We denote acceleration by A. If it is in vertical direction, we write AY. So that's the notation for acceleration in vertical direction. And for freely falling object, value of that acceleration is G. And direction is down. So that's how you want to remember. So if you're choosing up as a positive, then the acceleration would be, so that, see here, you can write like that, AY as negative G. So this is just the notation for this thing here. Whole thing is G here, okay? And the direction is this negative sign. So that's how it works for vector quantities. So it is different from scalars, regular numbers. So there is a question on the chat that says, why wouldn't you put the negative sign in front of A instead of Z? So why you don't put there? So that would mean negative of that acceleration. So you are negating that acceleration. So if acceleration is positive, then negative acceleration means, so for example, if acceleration was 9.8, then if that is AY, and if I write negative AY, that means I'm writing negative 9.8. Okay, that's what that means. We don't put in front of that. Okay. And then, so that's why we don't write like that. Okay. So we changing the sign by putting negative in front of AY. So AY itself has one sign. And if we put negative sign, that means we are changing its sign. That's what it means. So now, when it's coming down, so when I look at two of these, then what happens? Then the final, this is BF, this is BI. See, they are getting longer and longer. So that's that. So that means this gonna be delta V. So in this case, acceleration is still down. So see, the velocity while going up is up, but acceleration is down. Similarly, when coming down, both velocity and accelerations are down. So that's why it's speeding up. While going up, velocity is up, but the acceleration is down. So they are in opposite direction, means object slows down. That's what we learn and makes sense perfectly. So we're not just saying, we are showing it by drawing it, okay? Often we see confusion, and you need to be absolutely able to, like let's say, differentiate between acceleration and velocity. Velocity and acceleration, different things. Acceleration comes from not velocity change in velocity. It tells you how velocity is changing. So acceleration and velocity, they are not same. Although they are related, they are not same. just like your parent and you, related. You are not same, okay? Same idea. So make sure to differentiate, okay? So just like you and your sister or brother, related, not same. If someone says, hey, like let's say you have a sister, and then someone somehow, like let's say, think you are, not you are, but your sister. And your sister's name is, let's say, I don't know, Anna, but your name is different. So rather than, like saying you, hey, your name, rather if someone says Anna, see, that's not going to be right, right? Same thing here. Velocity and acceleration, they are related, not same. Make sure to differentiate that. Look closely. Acceleration tells you how velocity is changing, okay? So now with that, okay, this object is accelerating when it's going up, and the direction of acceleration is down. And when coming down, acceleration is still down. How about when it's changing direction? Let's say it went from, it was going up and then it started going down. So I'm looking at that situation here, turning around. So it was going up initially. Now it's going down. Okay, it's going down. What's the direction of acceleration? So we can say, okay, this is initial velocity, this is final velocity. Can you draw this change in velocity from these by using those two steps, tails together and from tip of initial to tip of final? Can you draw that? Try it. Are you drawing? I drew BI. Now you draw BF starting from the tail of that BI, and then draw delta V and see which way it's pointing. If it is pointing up, type up on the chat. If it's pointing down, type down, but make sure you draw. You should keep paper pencil near you, okay? If you are just watching this in one device and if you don't have another device to write on, you should keep your paper pencil near, okay? So I see mostly down. Okay, let's see if we get down. Let's see if I also get down. So BF is here. So if I draw or bring tail over here, I need to draw like that down, okay? So that's BF. So now that's the first step. So next gonna be drawing this one here, starting from tip of initial. So it's pointing down. You see that? Change in velocity. Although the velocities are shorter, see the change in velocity is still long. So that's why acceleration, value of acceleration is remains same even when it's turning around. It's not zero, okay? Okay, so here is a question for you. And you have total a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, now let's see, how did we do here? Mostly A and B. So both of them have A and B have S as the answer, but example versus not example. Okay. So what's the example that you can think of, folks? Can somebody tell that? What kind of motion is that? So I see one response that says turning around, another one says peak. Right. So when object is turning around and is at the peak, that's when we see zero velocity for momentarily, right? But non-zero acceleration. If acceleration was zero and velocity was zero, that means the object would be just floating there, okay? When acceleration is zero, velocity is zero, the object not gonna move, just like your car, not moving. So if you don't hit accelerator, it's not gonna move, okay? And free fall is another way to say it, yes. So yes, you should have example because we just talked about it, okay? So I think A is the best answer. B is also correct answer, but I'll stick with A in this case. You should have example because we talked about that. Roll a ball on the inclined plane. That is also an example, same thing, okay? So here is the graph, all these three graphs, position, velocity, you see that? Position, velocity, acceleration versus time. So this animation I slightly modified from the code I found online. Okay. So you can see how this graph looks like. I already talked about this graph in my previous animation, but here it shows you. Oh, oops, my bad. I did not mean to start the clicker, rather animation. I have to remove that question. Okay. Hopefully I remember to do that sometimes later, or I can do it right here. Okay. Okay, so let's run the animation. So see the object. So this is position versus time graph. Okay. And now this is velocity versus time graph, how it's coming down. And see how the velocity was going up and then came down. But the acceleration always, that here, white arrow always remains same, downward all the time. Okay. See, the acceleration remains same all the time, down and same, but velocity starts with up first and then turns around. Okay. So I see a question or something on the chat. If something is moving at zero speed, it cannot have a value of acceleration. Like throwing ball upward, there is an instant where velocity and acceleration is zero. When throwing, yeah, if you haven't thrown, then yes, okay, both velocity and acceleration zero there. But when it is at the highest point, when it is turning around, then acceleration is non-zero there. So that's what we emphasized. Yes, thank you for bringing that up. So it looks like we already have break time. So let's take a break, okay? So we'll talk more about free fall once we come back from the break. 5 minutes break. Okay, welcome back, folks. So I see Nicholas, has written nice thing on the chat. That's everything is written there is correct. But I am trying to avoid force at this point because we haven't talked about force. Or we don't talk about force until, like let's say, next week, I think. So that's why I'm trying to avoid force here. So I'm talking acceleration in terms of changing velocity. Okay. So now here is another question for you folks. And you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see how did we do here. So we got all responses, including 0, but there is slightly more for B. In this case, B is correct answer. Remember, this is velocity versus time plot. Oh, velocity versus time plot. So here, this here means there is no negative, means up is positive, okay? And how do we find acceleration from velocity versus time graph? How do you do it? How do we find acceleration? Slope, yes, exactly. So we look at the slope, okay? And this is sloping downhill, means negative, okay? So if you chose 0, you are talking about velocity. See, this reading is velocity, not acceleration. If you are trying to find acceleration from velocity versus time graph, you need to look slope. Okay? So that's why in this case, B is the correct answer. Okay, so now free fall, when something is in free fall, for example, sometimes let's say if we were to drop the feather and brick, same time, what happens? Brick arrives to the ground first. So it seems like heavier object falls faster. So that was the idea, okay? But Galileo later came up with this idea that everything falls with the same rate, okay? Here, feather is falling slow because there is air resistance on the feather. So when we had, like this Apollo trips on the moon in one of the Apollo mission, they brought hammer and feather and they dropped this on the moon and see what happened. So at that time, there was no HD camera, something like that, right? So this is the best video we have available, and this is in this link. Okay. We copied both solar wind and penetrometer drum in the EPD. Right, yes, I haven't put the solar wind in yet, but I will shortly. Oh, I'll watch this. Sure. Okay. A good picture, Dave. Beautiful picture, Dave. Well, in my left hand, I have a feather. My right hand, a hammer. I guess one of these. Can we copy both solar wind and penetrometer? Not here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than
on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So I don't know how good did you see, but both hammer and feather falling side by side. Why they do fall side by side on the moon versus, they don't on the earth? Because in the moon, there is very thin air, negligible air. Okay. Mm, so can you copy paste the link in the chat? I tried, but I have to exit from the slideshow to copy that. But I have posted these slides, PDF version of slide on the Canvas. You can copy from there if you like. Okay, it is class 4. That's posted there. Okay. On the moon, there is no gravity, which makes them the speed with them the same speed. So question mark there. So moon has gravity, but the gravitational force is smaller in the moon. So that's not the reason. The falling rate is same everywhere. There is a gravity, okay? But where there is air, what happens is air kind of gives you resistance for the lighter object that has larger area. So for example, this paper, if I were to drop something like that, it falls slowly. But if I were to drop something like this, then what happens is it falls a bit faster. If I were to fold it and then drop it something like this, rather than flat, if I do that, because air resistance acts on this area. Just like when you are driving car, when you are going faster, what happens? There is a lot of air resistance acting on the car in the opposite direction. So that's why even when you are pushing the accelerator, your car does not just keep speeding higher and higher, okay, because of that air resistance. So when you bring your hand outside, when it's moving, you can feel that air resistance in your hand, right? The same idea here. So there is some comment from Nicholas. Yep. So Nicholas, that's right. Thank you for writing that down. Okay. So now here on the earth, rather than doing feather and brick, if we can still try with two different objects, but that's not, both of them not feather wet, okay? Bit heavier, but we can tell from this picture, you can see the watermelon is heavier than, is that honeydew? So one is smaller, not that heavy. Watermelon is a lot more heavier than the other one, right? So if the heavier object were to fall faster, then here watermelon should be falling faster than that one, right? Let's see what happens. Don't blink. At the same time, yes. Okay. So it's not the heaviness that, making that difference in fall. But the Galileo at that time, more than 200 years ago, was able to figure that out. Object falls with the same rate. Okay, that's impressive, isn't it? Oh, no, I did not mean to do that. So now, just like solving any kinematics problem, this is also kinematic problem. Free fall is kinematics problem. So it is different than kinematics in this direction, in the sense that we already know the acceleration. We know the acceleration of free fall, okay? So now with that in mind, this is example problem from book. So it talks about, you know, the position and velocities at different time. So we can do one at a time. So for this time, we can find position and velocity and repeat that for this time and that time, right? But while solving this problem, what happens? Any kinematics problem, we sketch the situation. The sketch should have initial position and probable final positions, right? Something like that. It's not going to be that far, but I'm drawing something like that. So it's going to go up and then it's going to come down, but to separate from upgoing motion and coming down motion, upward and downward motion, I'm drawing it bit separately, okay? So final could be anywhere depending on the time, okay? Final could be anywhere depending on the time. So let's say for 1 second, the final is somewhere here. We don't know where it is, but anywhere. So we just want to fix that. So once we have that, sketch the situation, we need to write down the knowns and unknown. So this question is asking you among what are these variables? So y is for vertical direction and x is for horizontal direction, okay, in this notation. This is for horizontal, let's say, and this is for vertical. So among these, what are the things that we know are given in this problem? Because that's what we need to identify and write them down, right? Before we can choose the correct answer. So that's the question I'm asking you. And you have a minute. Oh, forgot to warn, 30 more seconds. Hey, I'm seeing need more time, so it's going to be total 2 minutes. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly C. Let's see. Person is standing on the edge of high cliff, throws a rock straight up with an initial velocity. So initial velocity we know, so that means VIY is 13 meters per second. The rock misses the edge and then falls back to the earth. Calculate the position and velocity. So that means final velocity in y direction is what? And final position is what? But if we say, okay, initial position, yi, wherever we, the rock is, if we start measuring height from there, we can always say yi is 0. That way, yf going to be same as delta y displacement, okay? So these are unknowns. So this is known. And what other things we know? Time is known. And since this is free fall, acceleration is always known. So this is known, this is known, this is known, okay? So final velocity, we need to calculate. We don't know, it's unknown. So that's why this is not correct. Again, final velocity is unknown, so that's why that is incorrect. This one seems to be known. Here, initial velocity in x direction, okay? So it's not talking about initial velocity in the x direction, but it clearly talks about initial velocity, this one. So I think this is best choice, just like most of you identified it, okay? So now, which equation to use then? Let's make a clicker question here. A, B, C. Which equation to use to solve this problem? Or there are two things, so I'll make it specific for position. Okay. So I'm opening the poll and you have 30 seconds. I'm polling on this one here. Five more seconds. 5, 4, 3, 2, 1, and it starts. Okay, so we know these three things. That has time and initial velocity, but there is no final velocity. So there is final. So that's not to use. Okay, let's see if we can use it. So position, final position, or displacement comes from here. Initial velocity is known. Time interval is given. Acceleration is known. So B is the correct equation to use. Oh, there was A and B competing. So why A is not right answer here? Can somebody explain why A is not right answer to find position? So there is no position information in this equation. See, this is final velocity, initial velocity, acceleration, time interval. There is no position. So we cannot use that equation to find position. But yes, you can use that to find velocity, where this one. So if the question was which equation for velocity, then it would be correct answer. Probably that's what you mistook with. Okay. So we now know which equation to use. It's time to use that equation. So delta y is VIY times time interval, initial velocity in y direction times time interval, plus half acceleration in y direction times time interval squared. Okay. So that's what that is. So in this case, initial velocity is known for 10 meter per second, And I'm doing this for 1 second, okay? For t is equal to 1 seconds. So that means 1.00 seconds plus half ay. Ay is g down. Here we are using this as a positive, up as a positive, y. So that means it's going to be negative g, which is 9.8 meter over second squared. And time is 1, so it's going to be 1 second squared, right? So now, this one, I think we can do it in our head. So this is just 13. This second and this second going to cancel. Meter. Excuse me. Oh, where did it come from? And half of 9.8 is, I think, is 4.9. So this positive times negative makes this negative. See, there is second is squared and there is second is squared. They cancel, giving you just meters. Okay, 5 plus 5 is 10. So 3 means, is that 8.1 meters? So if we look at this graph here, that's where that is, okay? So if you want to make graph, you need many points. So let's say here looks like it's calculating at half second, 1.5 second, 2 seconds, and so on, so that you can, make a graph out of that. So you can repeat this process for another times and then make graphs, something like that. It is done in the book. So I'm not doing everything. I'm just showing you one example here, okay? Okay, so 2 seconds, 3 seconds. Looks like Nicholas already calculated those values. So 3 seconds you see here, it is on the negative side, okay? So that's what you see in the graph. And now final velocity, how do we calculate that? We use this equation because we know acceleration, we know time, and so on, right? So initial velocity is 13.0 meter per second. And then see, this is negative 9.8. So I'm going to just write that down. And time is 1 second. Okay, so one of these seconds cancels. So 10 and 3 is 13, means 3.2 meter per second. Did I do that right? Something not matching there. What happened? Oh, 1 second, it's right there. So yeah, that makes sense. I was looking at 0 second, which is 13. That makes sense here, okay? So anyway, so that's how you solve for different things, okay, in free fall. So this is also kinematic equation, basically. So all we are doing is doing kinematic equation. So see if you can solve this problem without looking at, solution in the book, try that. Without looking my solution, you can repeat this one more time. So that's what you want to start. And then here is one problem I have done, which may be even easier than what we just talked about. So see, just look at this problem and see if you can find the, solve this problem, without looking at solution, okay? Try that and so on, okay? So now with that, we're done with just motion in one dimension. So that means so far we've been talking about object moving left, right, up, down, right, east, west, forward, backward. All those are one-dimensional motion, okay? We can label them as either X or Y. But what if the object moves not just in a straight line along just a line, rather it also moves sideways, okay? So that is two-dimensional motion. So for example, often our motions, they are two-dimensional, right? So we may be going east, and then we may start going south or north rather than just coming back, right? Usually we don't just go forward and then start coming back. We don't do that, right? And so we may start going in different direction. So that's what this example is about, okay? So I made this slide when, like sometimes I also teach in person. So physics classroom is in North Classroom building often. And next to the, in between that Learning Center building and the North Classroom building, there is a bus stop. And our class is somewhere here, let's say. And there are different ways you can come to the class. So let's say you got up from the bus and you want to come straight to the class, you can do that. And I'm saying, okay, that is. So this is your initial position. This is your final position, right? This is the initial. So you followed this path from the middle, straight path. So that's your displacement. A here represents your displacement. Vector A represents your displacement, okay? So now, let's suppose you wanted to grab a candy and there is a vending machine somewhere here, okay? And then what do? You first go there, B, and then C. Oh, so you went there first, got the, some candy from the vending machine, and you got to the classroom, okay? So now what is your displacement? Displacement is always from initial to final, isn't it? Straight line from initial to final. So displacement is still A. So now we need a math that gives us this B plus C is equal to A. That's the kind of math we need. Now let's suppose you want to run to the restroom before coming to the class, and restroom happens to be in this corner. And then you may go something like this, D, E, F. But your displacement is still same because your initial position is boss and final is that. So displacement is that. So that means B plus C should also give you A. D plus E plus F should also give you A. That's the kind of math we need. Okay. So ordinary numbers, if you were to add, you're not going to get this kind of result. So these being vectors, we call that vector addition. Remember, finding delta V, which is VF minus VI, it's a vector subtraction. Now we want vector addition. We want to add these two vectors so that we get answer. How do we do that? So if we pay careful attention, what do you see? First, let's look at B and C. So B, so tip of the B, and C I'm drawing, starting from the tip of B. So tail of the C is on the tip of B. Do you see that? For subtraction, we did tails together. Now, we do not want to do tails together because we're not subtracting them. We are adding them. So what we want to do? tail of second vector, and anyone could be second vector. Doesn't matter which one is first, which one is second. Tail of second is on the tip of first vector you draw. That's how you want to draw. That's what it is. See here, tail of C, second vector, is on the tip of B, means first vector. I'm talking about these two vectors, okay? So that's what you want to do. And that's what I have written here. Two actor, so tail to tip, okay? Move tail of one vector to the tip of next vector. Now we want this B plus C equal to A. See how A is drawn here. Where does it start? Where does the A start from? Tail of the B, right? And it goes to the tip of C. So tail to tip again. So you come back to the tail of first vector you draw and go to the tip of the last vector you draw. No matter how many vectors are there, you follow the same method. So for example, let's look at D, E, and F now. D, E, and F, right? See how tail of E is on the tip of D, and then tail of F is on the tip of E. And how do we draw that sum vector A? Starting from tail of the first vector we drew, here first vector is D. When we are doing D plus E plus F, D is first. So we start from tail of D and go to the tip of E, okay? Last one. Oh, sorry, F, I should say. Tip of F, last one, okay? Yes, Kiana, that's right, okay? Displacement is not always distance traveled. If something is moving in same direction all the time, distance and displacement happens to be same. But in other cases like this, displacement and distance, they are different, okay? As we can see here. So that's why we need a special kind of mathematics and a rule we need to learn, okay? So just learning how to add numbers not gonna be enough for this, okay? So these two steps, I'm copying that on the next slide and asking you a question. So there are two vectors. One is called vector number 3, okay, which is pointing to the right, and vector 4 is pointing to the up. So now draw them following this method, okay? Correctly draw them. Do not look at the choice for now. Draw them correctly using this method, and then look at which one has the purple arrow that is same as what you get, similar to what you get, okay? And you have 1.5 minutes total for this. It's just drawing 3 lines. Draw 3, draw 4 appropriately, and then draw the sum line, okay? Also called resulting vector. And 5 more seconds. Oh, 30 more seconds, sorry. Five more seconds. 5, 4, 3, 2, 1. and it stops. Okay, let's see what we got here. So A and B, they are competing. Okay. So, like many of you, if I am thinking A is correct answer, am I right or wrong and why? Can someone turn on microphone and talk about it? Let's suppose, like many of you, I'm also thinking A is correct answer. Am I right or wrong? Start by saying right or wrong.
Can you hear me?
Yes.
Okay. So A is wrong because you have to go from tail to tip, but the problem is that 3 and 4 are currently positioned with their tails touching. So you need to slide 4 over to where the tail of 4 is touching the tip of 3, and then you draw the vector from the beginning of 3 to the end of 4.
Oh, that makes sense. Here, tails are together. And then I'm going from tip to tip. But this is not what it is talking about. This is for subtracting vector, not for adding. So that's why I'm wrong. Okay. So what we have to do is slide this 4 to the tip and go like that. And this would be the correct way of drawing 4. And that way, that would be this. So B is correct answer in this case. Thank you, Nicholas, for explanation. Nice explanation. Okay. So we have to be careful. It's easy to get wrong. Okay, folks? So now, here is another question for you. Now you added 3 and 4, and this is what the drawing is telling you. How about the value of that vector, the resulting vector or sum vector? What do you think? You have just 30 seconds for this. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Less than 7 is A, 7 is B, and more than 7 is C. Okay, so A is correct answer. So 3 plus 4 is actually 5. 3 plus 4 is 5. So that's why for vectors, usually we do not want to write something like this. But if we write like this, then that is perfectly fine. So that's why the vector sign on top of those numbers, okay? Here there is no, because there is direction. But here, if you just look at it, you cannot tell if they are vectors or just numbers, okay? So in this case, the way these 3 and 4 are given, 3 plus 4 is 5. So how do you get that number 5? Using Pythagorean theorem. See, this is right triangle, right? So this makes right triangle. So this is like saying one side is square plus another side is square, right? So 3 square plus 4 square under the square root is 25, under the square root is 5. So that's how we need to get. And we can also find direction of this 5, what direction it is pointing with respect to 3 or 4. Okay, so we can do that. And Pythagorean theorem, if that sounds foreign to you, remember I posted a trick video, and I think I linked that to the pre-class assignment to this one as well. Okay, PC4, the link is there. And those all 4 videos were also linked in the home page where it says do the algebra and test or something like that on the module near the top of the module. Okay. So this is 50. That means actually 51. So that means that ends our class. So here is one example from MCAT. Now, what you want to try is see if you can do it yourself from the knowledge we have so far. Okay, so the slide is there. So you try that. So we'll pick it up from here quickly from here next class and then move forward. Okay, and we're going to talk about projectiles. Okay, folks, if you have quick question, just stay behind, or else we can you can leave, and I'll meet you next week.